Covalent bonding in the curious case of capricious hydrogen. You should be able to identify the conditions needed for covalent bonding. Draw the Lewis dot diagram of the diatomic gases hydrogen and oxygen. Nothing more than this, ever. Compare and contrast ionic and covalent bonding, and that's covered in the textbook, not in this lesson. Nonmetals, the ones in blue, can form covalent bonds. This does not include the noble gases, which do not participate in chemistry. Also, hydrogen sneaks onto the side of the table for some reason. It's normally hanging out with the metals, but it's definitely not a metal. So in fact, chemically, 99% of the time you react with hydrogen, you're dealing with it as if it is a halogen, a salt-making material. Except your stomach barf, which is hydrogen chloride, which is an ionic compound of acid in your stomach. Boron is out of there. It's too complicated to deal with, in fact, in most of high school. The Lewis dots of these columns are as so. Everything in this column has this Lewis dot. Everything in this column. Everything in this column. There are not an infinite number of patterns. There's not even the 92 on the main table. Learn these patterns. One column, one set of Lewis dots. All of these here are closer to having full valent shells. And out of these, we're only going to be looking at these guys. And the ones I really want you to be able to do is oxygen and hydrogen. That'll serve you right up to grade 11. And the rest are just replications. So it gets really simple. Normally, how would you fill a valent shell in something like chlorine? Well, something like sodium would come along going like, yo, I got a spare electron in my outer shell. He ain't doing nothing. Chlorine's going, I would love to fill my spot with an electron. And they would bond ionically. Sodium becomes positive 1. Chlorine comes negative 1, and we had a nice donation. You line up your empty spot, you put your 1 extra electron here, you pass over. And the whole conglomeration, he's plus, she's minus, adds up to 0. That's not the case when they both want. When they both want, they sort of get into a tug-of-war. You give me yours, no, you give me yours, and they pull to a stalemate in the center. But this is the school system, and we're not supposed to admit competition. So we say they got together and they shared. They shared like Care Bears to the middle of their, their orbits, right? So it's a shared thing. Now, in sharing, cheapskates win. Everyone hates it when you go to someone and they go like, can I try one of your french fries? And you go, sure. And then they turn around and grab 4 of your meatballs and you're like, whoa, 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 whoa. So the sharing has to be carried out by rules of equity and fairness. Oh no! What happened to this slide? That's better. It was supposed to be in first. Now, let's look at these things so-called diatomic gases. Diatomic gases mean 2, not die! Atoms die! Alright? You are supposed to know that all of these appear in pairs, like pants, like other things. N2, O2, H2, F2, Cl2, Br2, and I2 if it's a gas. Come on, it's not hard to remember that. When you write them down by themselves, you've never heard a doctor go, nurse, get him some O. It's like O2. You just think about that. You've never seen oxygen as a formula written any other way than O2. This only applies while they're by themselves. If they are mated, then the rule isn't there anymore. They're not alone. So H2O, you don't have to forcibly make the 2 on the O. And rest is Fe2O3. It's only when they're isolated by themselves. So this would be a testable one. This is as hard as it can get on any test in grade 9 and in grade 10. I want you to be able to do more, but this would be sufficient on a test, even the final exam. The 2 chlorines are going to meet and they're going to bond to each other. They're going to form Cl2. 2 things we have to do. Get the empties to the outside. Move them away. There isn't an electron jumping to an empty spot. If this was an ionic bond, this would be disastrous because you'd be drawing this electron traveling way over here and in. No. Put the empties out of the way. and leave enough room for Bohr and Rutherford in between. Now we're ready to start playing. It's like football. Would you like an electron? I would love an electron. So would I. Maybe we can get together and share. Oh, that would be wonderful. Okay, Chloretta. Here, I shall lend you an electron. Oh, that's so sweet. Now, you're going to draw it like that. You're not going to need a colored circle. You're just draw an X, right? Because you're not doing this on animation. Then Chlorina goes, oh, Chloretta, it is so kind of you to share one of your electrons with me. I shall reciprocate forthwith. And it gets drawn like that. Now, how do we double check we did this right? I'm going to erase where the electrons were. You can't do that. I just want to clear it up. Those two electrons move forward. So now we've entered a shared state. And let's see if chlorine managed to get 8 electrons. 1, 2, 3, 4. 5. 6, 7, 8. How come I didn't count this one? Because it's not there anymore. It moved forward. But in your diagram, you're going to still have those electrons there, and it's really easy to overcount. So this is what you can see unless you can erase that spot. And so it's very easy for a student to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't double count. So this is chlorine gas, Cl2. That's what you smell when you're in a swimming pool. That's as hard as it can get. What about oxygen? Oxygen's O2. In this case, both of these have a valence of -2. It's on the table. You can use the table anytime. Now each one wants 2 electrons. So if they want 2, they must share 2. So it passes the electron forward, which you're just going to write like that. Then the other one reciprocates. Passes an electron forward, it looks like that. We do it again. And a 4th time. I'll put those highlights back in because you will be left with that. And there's our finished diagram. And that, again, I could ask you on a test. But if you can do Cl2, you can do O2. It's really no difference. The next one would be nitrogen, and it's just going to be 3 and 3. Just when you go to count electrons, don't go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dang, it's got 10. No, these move forward. They're not there. Now let's go into territory you're not going to be asked to do. This one. Oxygen dichloride or dichlorine oxide. It's ugly either way. Never, ever, ever in grade 9 or 10 would we generally ask you this. This would be like serious bonus advanced kind of stuff. And certainly not grade 9. So you can go like stick your fingers in your ears and go la 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 la. I don't want to do this one. But it's not terribly hard. When the numbers are different, okay, the cheapskate wins. Oxygen wants 2 more to fill its valence shell, so it will share 2. But chlorine only wants 1, so it will only share 1. The cheapskates wins. If someone says, hey, we're going to go on a picnic together, why don't we chip in some money and we'll share? And you go, I'm willing to put in $10, and your friend goes, I'll put in 5, and you're like, well, screw you, I'm not giving you 10 then. So the cheapskate wins. Chlorine goes, I'll share 1 with you, and oxygen's fine. I'll share 1 back. Now this chlorine's content, going, I've got my 8 electrons. But the oxygen is like, this kind of sucks. So it's going to need a second chlorine to come in, and the second chlorine go, well, I will share 1. And between them, oxygen has now managed to gain 2 electrons by pretense, by this shared pool. See? 2 electrons are coming in. This means oxygen's a playa. He's got 2 girls, or it's a girl with 2 guys. So oxygen has 8 in this zone. 1, 2, 3, 4, 5, 6, 7, 8. Don't double count. And each of the chlorines looks like it has 8. 1, 2, 3, 4, 5, 6, 7, 8. This is why you must participate in this stuff. You walk into a classroom and the teacher's got this on the board and you didn't see it getting drawn, it's a nightmare. Trust me, these things are way easier to create than mark. But again, this is not grade 9 now. I would not ask you this. I'm just pushing you. As my theory goes, if you have to lift 100 pounds in a competition, you better train at a 150. So if you can do this and follow it, you're like solid for grade 10 academic. If you can't follow it right now, still doesn't mean you can't do grade 10 academic. It just means that I'm pushing you just at the edge of your boundary. So let's push a little bit more. What do we call this molecule? Naming schemes are used in grade 10. Here it is bonus in grade 9. Science never really got clear on this, and we couldn't decide whether it was dichlorine oxide or oxygen dichloride. Both names work. Most of you would probably go, I guarantee it, probably go, I don't know, oxygen dichloride just sounds nicer. Think about that. Do you find dichlorine oxide or oxygen dichloride to be a nicer sounding name? And 99% of students would say they like this one. And you know what that shows you? You actually have learned a little bit of chemistry over time. You've learned enough, without even realizing you've learned it, to actually go, it doesn't sound right. You can't come to that conclusion unless you had some foreknowledge in your brain. So whether you wanted to or not, you've absorbed some chemistry in life. Let's try selenium chloride. What kind of bond are they going to form? I don't know. We have selenium there. It's right on the right side of the nonmetals. And there's chlorine, so technically they should be a covalent bond. If it was tin over here, married to chlorine, it would probably be ionic. I don't know. We wouldn't put you in such a situation to identify the bond. We'd tell you what kind it is. There are 3 ways we can get a valence now for these. The first way, if you want to waste a lot of your time, is to draw the entire sequence of events from the atomic tile to the abbreviated Bohr to the Lewis dot. But unless we have asked you to do so, you are not required to produce this. And it only works up until element 21, and selenium is beyond that. This is why we let you use the textbook and the table that has the valence printed on it. The second way of doing this is count from the end of the table. No empties, 1 empty. No empties, 1 empty, 2 empty. And it doesn't matter if I wasn't pointing at the row of selenium, since it applies all the way down. So selenium will have 2 missing electrons. The final method would be to read the valence table that you are allowed to use on any test or exam. And they would state this. There won't be any mystery to get these valence numbers. The long approach only if required. We're down to here now. We've got our 2 valences. We can start to draw the diagram. So I lay them out. Hey, it's looking exactly like the setup for oxygen and chlorine. Wait a moment. It's exactly the same. 1 each. She looks like she's got 8 now. So does... What sorcery is this? It's exactly the same as the oxygen one. Yeah, because selenium's in the same freaking column. So of course it's the same. Right? Now, does this exist? I don't know. Is it selenium dichloride or dichlorine selenide? What's correct? Well, this is the thing where chemistry advances. They go looking for it and go, guess what I found? You won't believe what I found. There's at least 3 different variations of this thing that I can't figure out. I found selenium dichloride, and I found diselenium dichloride, and I even found selenium tetrachloride. How am I going to figure out this? If you look at these, you'll discover that you can only make a Lewis dot for one of these things. It's just not going to work. You can do this first one, but you'll never figure out this one with grade 9. Welcome to the club. What do you think scientists have to go through? They have to keep running into situations where they don't have an answer. They can't go look it up. They have to figure it out. Now, if you're really clever and you're really keen, you might figure out a means of solving for diselenium dichloride, Se2Cl2. But I would be stunned. It would take a very rare student to be able to figure this sucker out on their own, because it's sitting somewhere between an ionic and a covalent bond. And you'd have to really think about something like O2 again. Remember, selenium is just below oxygen, and there might be a trick. If you can figure out this one, you're like totally ready for grade 11 or 12. And you email me if you want to give her a try. Hydrogen is wonderful and wacky. It can show up as +1, behaving like a metal. It can show up as -1, behaving like a gas. In this one, it would donate the electron to empty its valence shell, or it could gather an electron to fill its valence shell. And it's smack in the middle, so it really doesn't matter. Does it give or does it accept? It'll do both. And you get into grade 11 before we really get into that. There's a slight hint that is absolutely irrelevant to you in grade 9 and 10, because we'll tell you what we want. But the odds are, if hydrogen leads the formula like HCl, then hydrogen is behaving like it is on the left side of the atomic table, like a metal, like lithium and sodium underneath it. But if hydrogen is written on the right side of the formula, like NH3, then hydrogen is behaving like it is on the right side of the table, with fluorine and all its friends underneath it. And it ain't consistent. This is just one of the little rules they forgot to tidy up. I will have an extension on hydrogen, hydrochloric acid, and methane for those of you that want to pursue grade 10 and grade 11 while we have this extra time. In the meantime, chemistry's a beach. I think you all agree that chemistry can be a beach. And I'm going to show this to you literally. I was going to say littorally, but none of you are doing oceanography. But if there are any oceanographers watching this, I said, chemistry is a beach littorally, they'll probably go like, that's a good one. Silicon dioxide. Silicon dioxide. You've heard of carbon dioxide, which is that what? CO2? So silicon dioxide would be SiO2. We need to look up the valence before we can do this. Oxygen says -2 in your textbook, but there's nothing written for silicon, just a dash. How do we figure out silicon? Well, we count. If we look at the table where silicon is, it's 1, 2, 3, 4. Along. So it has 4 electrons. Or Kaladi notation, you could say it's missing 1, 2, 3, 4. So she's smack in the middle of the table. It has 4, it's missing 4. It's not that hard to figure out its valence. Who needs the grade 11 textbook with the actual numbers there? So we got 4 valence electrons. Now, suppose you still don't want to learn the simple way and you're like, no. I want to not pay attention and I want to learn this as hard as it can. And the last thing I paid attention to was Bohr-Rutherford diagrams. So knock yourself out. If you really want to, look up the numbers. Make your little nucleus. Populate your electrons. Make your Lewis dot. You know, it's like, I'm sorry, I know us teachers sometimes want you to be able to do things quickly, but if you really want to do it the long way, that's how you can. But otherwise, just freaking count. 1, 2, 3, 4 missing. Done. Oh, well, look at this. It's already been set up for you. When did that get there? I don't know. I want 4, I want 2. Cheapskates rule. The oxygen will pass forward 2 electrons, and silicon will say, no problem, I'll share with you. There's 2. Done on the one side. Same thing happens on the other side. Which notation would I prefer you use? Most textbooks do this. I'm notorious for not leaving room between my diagrams, and I often stack them like that. Either way works. And then we do our, like, Olympics. Silicon now has 8. Okay? Remember, 4 here, 4 there, that's 8. These 4 don't make 12 because they moved. They're not there anymore. And the oxygens are done on this side. It's like the Olympics, but with only 3 continents. We have these sharing zones. So that's our silicon dioxide. Now what if I said you can't leave the classroom until you do silicon dioxide, carbon dioxide, germanium dioxide? Guess what? When they're in the same column. They have the same freaking valence almost all the time. So once you know one, you can just swap out the letter. Then if I say, curse you, child, you solved it. You can't leave that until you do carbon disulfide. Woo! Sulfur's right underneath oxygen. You just switch the letters. It's not going to change. The staircase you got to watch. But seriously, if you were able to draw carbon dioxide, you can do silicon dioxide. If you can do carbon dioxide, you can do carbon disulfide, carbon diselenide. That's the whole point of the table. Okay, please. It's always that small percentage of students that just keep acting like they don't learn anything because you're not paying attention for this pattern. But let's go back to silicon dioxide. What is it? What does silicon dioxide look like? It's this! Its common name is silica when it's powdered. You know it as the mineral quartz. And that's the white grains in sand. When you go to a beach, it's silicon dioxide. So that's what I mean. Chemistry is a beach. Now, the little dark particles, you can watch my video on magnetite, iron oxide. There's granite parts and probably like human body parts from a long time ago. The only other possibility for the sand to be white is it's chalk, calcium carbonate, which means it's made up of bones. Not people bones, but bones like from sea creatures and shells and stuff. But you pretty much pick up sand and you can tell. If it feels chalky, it's a chalk beach and it's going to be all mucky and gross and slippery. And if it's a quartz beach, it's going to be all gritty and you won't like it in your pants. Okay? So a beach is silicon dioxide. Here's another one. 60% of the planet is silicon dioxide. Sand. We're on the sand planet. And again, I guarantee you this picture here, that's quartz. This one could be chalk if I already didn't know it's quartz. So this is silicon dioxide. These ones in England, that's definitely chalk. That's the White Cliffs of Dover. So now you're looking at a chalk coastline. And you can, if you were there and you could touch it, you could easily tell the difference between a chalk beach and the silica beach. The chalk beach is going to be more like clay, mucky. Ooh! Someone killed a kraken here. How did this sand get pink? Remember, I'm colorblind. Well, again, silicon dioxide is white. So a tinge of some other metal in there, like chromium or iron, and it causes the silica to change color. Oh, it's like someone murdered a monster in there, right? So, again, this is a quartz beach. It's silicon dioxide. This one is not. This beach is made out of magnetite. That's the black crud inside the sand that I used a little magnet to find out. So this is a magnetite beach. Good luck being on this beach and trying to use a compass to navigate. So yeah, you can have a black beach and all like those like goth kids could go be like, the black sand mirrored the darkness of my soul. And you're going to walk across this beach real fast because it's going to be hot potato on that beach. Oh, green. Green. I can see that shade of green. This is olivine. And it's another silicon-based thing, but not silica. It's silicate. And what's the difference? Well, stay tuned for grade 10. Wouldn't that be awesome? That it kind of makes me feel barfy. But you probably didn't realize it's green sand beach, and it's not moss, it's not fungus. It's this gemstone called olivine. All right? Now, this is the part that really flips me out. Here's like somebody's like chili pepper, chili powder, whatever. It's chili pepper, salt, maltodextrin, spice, onion powder. And then we keep on going down the list. Partially hydrogenated soybean oil, yeast, silicon dioxide. What the heck is silicon dioxide doing in my food powder? They put sand in the food powder. And if you turn over a great deal of your spices at home, if you buy salt, if you buy a bag of flour, almost every last one of them will say silicon dioxide. And there are people out there that are just going nuts about what silicon dioxide being put in the food. And they've actually had to show you the answer because of the complaints about it. Because of this online conspiracy theory, they put brackets, anti-caking agent. You mean it won't let you make a cake? No. What it means is it stops it from clumping. You've all probably had some sort of spice like garlic powder, and you went to shake it out one day and it was like a solid brick. Well, you put in some sand, the white crystal sand things, and it will cause it to stop sticking together. If you turn over Fido's flea powder, any kind of powder you can sprinkle on a person, you know, like talcum powder or whatever, they'll all say silicon dioxide. So they put in very finely ground sand, and that keeps it from sticking together. And silicon dioxide, quartz, beach sand, that stuff's been around since the beginning of time. It's nearly indestructible, so it goes right through you like when birds eat their little stones. You'd never even notice. Go online and type in why is silicon dioxide in my food, and people are losing their freaking minds over it. So I'm going to show you a little bit more about silicon dioxide because it is freaking awesome, all the things that it shows up in. And almost nobody knows it's just sand.